Section 19. CMB Variations and Baryon Acoustic Oscillations, BAO. The Cosmic Background Explorer, or COBE, satellite in the early 1990s confirmed that the CMB signal from patches of the sky has a near-perfect black-body spectrum corresponding to a temperature of 2.7 Kelvin. The WMAP satellite in the 2000s had better accuracy and better angular resolution than COBE. These next images are the temperature of the microwave signal received from different directions of the sky by WMAP. Red is warmer than green, blue is cooler than green. So at some level of contrast, the entire sky looked to have the same temperature. Now, let's look at the second amplified image. This has higher contrast than this image. The red area in the upper right and blue area in the lower left are due to a dipole Doppler shift due to our peculiar motion with respect to the universe, which astronomers can correct for. Earth is moving 30 kilometers per second in its orbit around the Sun. The Sun is moving 250 kilometers per second in its orbit around the Milky Way. The Milky Way and Andromeda are moving toward one another at 123 kilometers per second within our local group. Our local group is moving within the Virgo supercluster. The Sun's net motion is 370 kilometers per second with respect to the cosmic microwave background frame of reference, or 0.12% of the speed of light. And that is this red and yellow and violet, blue, and cyan component. And scientists can remove it. This third image has that dipole component removed, and the contrast is then increased by another factor of 100, and we get this image. The red horizontal band across the middle is non-thermal emission from gas and dust in the Milky Way. This fourth image has that component removed. Then, the microwave background is thermal in every direction, but with temperature varying slightly in different directions. Hotter here, colder here. Here are the highest resolution temperature results from the Planck satellite, with the Milky Way anomalies processed out. The red regions, slightly higher temperature. The blue regions, slightly lower temperature. Large area lower temperatures, lower energies, here, are believed to have been local overdensities of dark matter, a deeper gravitational potential well that the photons needed to get out of, and they lost energy in the process. And large area higher temperatures, higher energies, this large area, are believed to have been local underdensities of dark matter. The average temperature is 2.7255 Kelvin. The variations are within 10 parts per million. At CMB last scattering, our visible universe was uniform in temperature, energy density, and matter density to within 10 parts per million. We could stop here, but the variations help cosmologists model the composition of the universe and check their models. Large areas are slightly warmer or slightly cooler than average, but there are also slight warm and cool variations on every scale down to the limit of resolution of the Planck data. There are little blue dots and little red dots. The remainder of this video might not interest you, in which case skip to the next video. The temperature variations get processed into a correlation function, which tells how the variations correlate between all pairs of points in the sky as a function of the angle separating the pairs of points. For example, the dipole variation is a strong magnitude of correlation for pairs of points in opposite directions, 180 degrees apart. But that signal gets removed from the analysis because it is solely due to our peculiar motion, not the composition and expansion of the universe, and so we can see smaller signals. This graph is called the power spectrum of the CMB temperature variations from the Planck data, and it tells cosmologists a lot about our universe. Each angular scale on the horizontal axis, 90 degrees, 1 degree, tenth of a degree, corresponds to a physical size on the last scattering surface and a particular size presently. The European Space Agency website says, the green curve represents the best fit of the standard model of cosmology, currently the most widely accepted scenario for the origin and evolution of the universe to the Planck data. The pale green area around the curve, this area, shows the predictions of all the variations of the standard model that best agree with the data, while the observations on small and intermediate angular scales agree extremely well with the model predictions. The fluctuations detected on large angular scale, lower left on the graph, are about 10% weaker than the best fit of the standard model to Planck data. At angular scales larger than 6 degrees, so left of my cursor, there is one data point that falls well outside the range of allowed models. These anomalies in the cosmic microwave background pattern might challenge the very foundations of cosmology, suggesting that some aspects of the standard model of cosmology may need a rethink. For angular scales greater than 1.1 degrees, multipole moment L less than 160, left of the vertical dashed blue line on the power spectrum graph, CMB cool spots are believed to have been slight overdensities of dark matter at that time. Photons lose energy escaping the gravitational well. And CMB warm spots are believed to have been slight underdensities of dark matter. In this region of the power spectrum, temperature and density fluctuations are low, but there is scatter in the data. There is opportunity for improvements in measurements and of cosmological models. There is a cosmological problem with uniformity on scales larger than 2 degrees, called the horizon problem, which we will cover later. On smaller angular scales, less than 1.1 degrees to the right of the blue dotted line. The temperature fluctuations are believed to be due to Baryon Acoustic Oscillations, BAO, and the data match the green curve very well. Immediately prior to photon decoupling, the photons, electrons, and hydrogen protons constitute a single coupled fluid whose energy density is only 40% that of dark matter. The photon baryon fluid starts to flow toward dark matter overdensities, gravitational wells. However, as the fluid is compressed by gravity, its temperature and radiation pressure rise with its density. The temperature and pressure cause the fluid to expand outward. Fluid expansion causes the temperature and radiation pressure to drop, and gravity causes the fluid to flow inward again. This inward and outward cycle of the photon baryon fluid is called Baryon Acoustic Oscillations, or BAO. If the fluid is at maximum compression at the time of photon decoupling, the photon temperature will be slightly warmer than average. If the fluid is at maximum expansion at the time of photon decoupling, the photon temperature will be slightly cooler than average. The first peak, here, at multipole moment L around 220 and angular scale 0.8 degrees, represents those dark matter overdensities for which the photon baryon fluid had just reached maximum compression at the time of photon decoupling. The angular size of the first peak tells cosmologists whether the curvature of our universe is flat, positive, or negative. Data is consistent with zero curvature, flat. The amplitude of the first peak tells cosmologists the baryon density of our universe and is consistent with baryons being 4.9% of the present energy density of our universe. The size now of the region corresponding to this angular scale of the first peak is about 200 megaparsecs, large enough to include galaxy superclusters and cosmic voids. The size now of the region corresponding to the angular scale of the third peak, here, is about 55 megaparsecs, roughly comparable to a single galaxy supercluster or cosmic void. Astronomers are looking for rings corresponding to the BAO peaks. These images are an illustrative visualization, not actual data. The left image shows the CMB variations due to the first peak on the left of the left image, so here, versus with no peak on the right, here. So with that peak, we see bigger and brighter red and blue spots. The right image shows the CMB variations due to the third peak, this peak, on the left side of the right image, versus with no peak on the right. The peaks increase the magnitudes of the variations. This graph shows possible energy densities of the universe as a fraction of the present critical energy density, with matter on the horizontal axis and dark energy on the vertical axis. So this point at the lower left would have a matter energy density 0.2 of critical density and a dark energy density of 0.6 of the critical energy density at the lower left. The area within the long light gray bubble is the 95% confidence level from the data from the CMB combined with type 1a supernova data. The area within the black bubble is the 95% confidence level combining CMB, supernova, and BAO peaks data. The dashed line represents zero curvature, a flat universe. From this data, cosmologists believe that our universe is 13.78 billion years old, flat, at critical density, with 68.9% dark energy density and 31.1% matter energy density presently, and that dark energy density is constant with scale factor and time, but cosmologists will continue to seek higher confidence levels from data. This is the end of our material on the CMB and BAO.